Okay, so let's take a look here at a few of these examples of compute the derivative of the given function. So now this is asking us to use the definition here. So in this case, how we get it to memory, we write it down and we would say f prime of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x all over h. And so let's take a look here at example number 4. So this is where it gets where the heavy lifting, because now you see that this is going, wherever you see an x, you're going to have to replace with x plus h. So this is going to require us to write down the limit notation as h approaches 0. And so this x, so now what do you have? You have this to be a 2 minus, this is going to be a 7, but what are we replacing here? We're replacing this with x plus h, and we close this out. By definition here, we have a minus, and then we replace all of f of x. So all of f of x is all of this, and this is going to be minus a 2 minus a 7x. And then this is going to be all over h. And now you see here, right, this quantity is, as we said before, this is called the difference quotient that we would need to simplify. So there's a couple of things that we would need to keep in mind. We still need to write the limit as h approaches 0. Now what are we going to do? We are going to distribute there. So what is that going to be? This is going to be 2 minus a 7x minus a 7h. Then we have to distribute here, minus 2 plus 7x, which is going to be all over h. And what do we have? We have, this is nice because this is going to reduce with this. This is going to reduce with this. And therefore, you get the limit as h approaches 0 of a negative 7h all over h. And this is what we want. We need this h. We need this h to reduce out. And now they're going to reduce out. So therefore, you're going to have the limit as h approaches 0 of a negative 7. And as we said last time, the limit of a constant is going to be a constant. And what do we have here? This original is saying that we have f prime of x is going to equal a negative 7. And as we finished up class last time, anytime you have something linear, well, the value in front of x, that represents slope. So we could predict it that the slope of this linear function was going to be negative 7. And so now what they're asking us a step further is now find f prime at negative 1. But when you evaluate negative 1 with a constant, then you're going to get that constant. So this was two parts. Find the derivative with respect to x and find the derivative at that given value, that given point. And this is where the heavy lifting, we're not going to want to have to use this limit definition every time, because that is going to require a little bit of work. So what I recommend is that practice for problem number 3, going through this process to predict that that slope should be 5. And if you're not getting 5, then that's going to tell you that something went wrong in your algebra. So that's dealing with what is called a linear function to find its derivative. Now, if you scoot this over, no, that's my YouTube. I want to go back. Someone said going back between the windows is a little confusing. I do apologize, but at this rate, we're kind of restricted on what we have here because of the windows. So I just want you to see that this was 1, 2, 3, 4. Now the functions 5, 6 are going to be quadratic. And then what happens when you get to these types of functions? That's why we want to talk about the differentiable rules that we're going to get into as well. So let's take a look here at number 6. F of x is equal to x squared minus 1. So f of x equals x squared minus 1. So f of x equals x squared minus 1. And so in this case, the last example, we used f prime. In this example, I want to use dy dx, because what's going to happen is that these functions are not going to always be written, and we need to be able to interpret. So again, we write dy dx is going to equal the limit as h approaches 0 of f of x plus h minus f of x, which is going to be all over h. And you're saying, like, where did this h come from, right? Well, this h is taking in consideration that in our previous definition, you remember when we had f prime of a, and we're taking a look that this is going to equal the limit as x approached a of f of x plus a minus f of a all over x minus a. So in this particular case, math, right? We like to keep things, we try to keep things simple, but then we're not. This x minus a now is getting replaced with the h. And what we're trying to do is we're trying to take those, because remember, this represents the average rate of change, which is the secant line. And actually, this is not it. Sorry. So what this is going to represent here is that this is representing the secant lines. And what we're trying to do is get closer and closer and closer to the tangent. And that is what this is doing, is driving those secant lines to get closer and closer to the tangent. And so just like we saw above here, I want to make sure I'm getting everything in the window, is that now you have to replace this x squared with this x plus h. That's the heavy lifting, because when you write this, the limit as h approaches 0. Well, now you're taking that x and you're replacing it with x plus h. At the same time, you are now going to square it, but you can't forget that we still had this minus 1 here, and that's what all of this represents. Then by definition, we are subtracting, and then we're subtracting f of x, which is x squared minus 1, and this is going to be all over h. And so we had a problem, I think, similar as a limit, and I'm noticing that here you have to be careful that this is going to require us to multiply x plus h times x plus h. And so the limit as h approaches 0, and if you write that out in space, x plus h times x plus h, distribute, 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 combine like terms, you're going to get x squared minus plus a 2xh plus an h squared. This is still the minus 1. And then when you distribute here, you get a minus x squared plus 1. And then that's still going to be all over h. And you see how the work just intensified from going from linear to quadratic? So imagine if this becomes cubic or this becomes radical. It just becomes a little bit more work involved. And so again, keep in mind, we're always trying to get this h to cancel, but you have to do it with the proper steps. So this is nice that this and this is going to cancel. This and this is going to cancel. And so when you rewrite this, you're going to have the limit as h approaches 0 of 2xh plus h squared all over h. And a lot of things is that you cannot cancel over addition. I didn't make the rules. It's just like you can't make a U-turn in the middle of the street. You could get a ticket. It's kind of like that. And so unfortunately, you factor out the h, and that will be 2x plus h all over h, and you reduce. And therefore, you get the limit as h approaches 0 of 2x plus h. And now when you use your direct substitution, you get 2x. So what this is saying here is dy dx is going to equal 2x. That represents the slope at any point. And if you go back over here to that problem, out of my time of 10 minutes, it said that x was -1. So typically when we have a function in dy dx and we evaluate dy dx, we typically write here this little bar, and we say x equals -1. And you replace -1 here, then you get to be a result of a -2. So this indicates that your slope of the tangent line is -2. At the point. So you remember they said x is -1. So at the point -1, but then you have to go back here to your function. And if you put a -1 here and you square it, you get 1, and 1 minus 1 is 0. So the slope of the tangent line is -2 at this point. would be interpretation. And so you could see it is a little heavy lifting, right? Because what would have occurred if they gave us the function, let's say f of x equaled 2x squared minus 5x plus 3, and they wanted us to find f prime of x. Well, we would have to use f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And wherever you see an x, you're going to have to replace x plus h. And so that would be the limit as h approaches 0. And then this would be a 2 times x plus h quantity squared minus a 5 times x plus h plus 3. And this will be minus f of x, which is 2x squared minus 5x plus 3 all over h. And we would have to simplify. It's doable, it's doable. It's just it's more work involved. Just so that we could do all these steps, and I could tell you that f prime of x would be a 4x minus 5. Do you want to go the long version or do you want to go the fast version? I think fast. Right? And that's what we're going to do, is talk about the different differentiation rules to find the derivative of a function that represents the instantaneous rate of change at some given point on the curve of the original function.